Hello everyone. Today we'll study elementary matrices. Before I introduce what is an elementary matrix, let me first of all recall one thing which we learned in our first class. In our first class, we learned that there are three elementary row operations on a matrix. First operation, in a matrix, we can multiply a row by a non-zero constant. Second operation, in a matrix, we can interchange any two rows. Third operation, in a matrix, we can multiply a row by a constant and add it to another row. Those are three elementary row operations we learned in our first class. Next, let me introduce row equivalent. What does it mean? Let A be a matrix. If matrix B can be obtained by performing a sequence of elementary row operations on A, then we say matrix A and B are row equivalent. So, let A be a matrix. If I can perform some elementary row operations from here, if I can perform some elementary row operations, if I perform some elementary row operations on A and obtain B, then we say matrices A and B, they are row equivalent. Let A be a matrix. If we perform a sequence of elementary row operations on A and we obtain B, then we say matrices A and B, they are row equivalent. Next, let me show you an example. Consider this matrix. Let's call this matrix A. If we try to do some operation on A, what operation can we do here? Let's try to reduce A to the reduced row echelon form. So, in order to reduce matrix A to the reduced row echelon form, in the first row, we try to make the first entry to be a 1 here. How can we make 1 here? To make it easier, I can interchange row 1 and row 3. That's elementary row operation. Interchanging two rows, that's elementary row operation. I can interchange row 1 and row 3. I get 1, 2, 2, negative A. Second row stays the same. For the third row, I put the first row here. I get 2, 4, 0, A. Next, since this is a leading one, we try to make all entries below leading one to be 0. So all I can do here is I can multiply first row by negative 3, add it to the second row. Let's do one operation in a step. Here I leave the first row the same. I multiply first row by negative 3, add it to the second row. I got 0, 0. Negative 3 times 2 is negative 6. Negative 6 plus 2 is negative 4. Negative 3 times A times negative A is 24. 24 plus 0 is 24. Let's do one operation in a step. So I leave the third row the same here. Let's do one operation in a step. Next, I try to make 0 here. So I multiply first row by negative 2, add it to the third row. First row stays the same. Second row stays the same. Negative 2 times 1 is negative 2. Negative 2 plus 2 is 0. Negative 2 times 2 is 4. It's negative 4. Negative 4 plus 4 is 0. Negative 2 times 2 is negative 4. Negative 4 plus 0 is negative 4. Negative 2 times negative 8 is 16. 16 plus 8 is 24. Now we are done with the first row. Next, let's move to the second row. In the second row, we try to make the second entry to be 1 here. Is it possible? Is it possible that we can make the second entry to be a leading 1 here? Since all entries are 0 here, so it's impossible to make a leading 1 here. Next, let's move to the third column. Is it possible we can make a leading 1 here? Here I can divide the second row by negative 4, which means multiply second row by negative 1 over 4. we can multiply a row by a non-zero constant. That's elementary row operation. Multiply second row by -1/4. So first row stays the same. From the second row I get 0, 0, 1, -6. Third row stays the same. I get 0, 0, -4, 24. Now this is a leading one here. We try to make all entries above and below leading one to be 0. Let's try to make 0 here first. So all I can do is I can multiply second row by -2 and then add it to the first row. That's an elementary row operation. So here I leave the second row the same. 0, 0, 1, -6. Multiply second row by -2, add it to the first row. Get 1, 2, 0. -2 times -6 is 12. 12 plus -8 is 4. Leave the third row the same. I get 0, 0, -4, 24. Next, we try to make 0 here, which I can multiply second row by +4 and then add it to the third row. Multiply second row by +4 and then add it to the third row. So I leave the first row the same. 1, 2, 0, 4. Leave the second row the same. 0, 0, 1, 6. Multiply second row by 4, add it to the third row. 0, 0, 0. 4 times -6 is -24. -24 plus 24 is 0. So we are done with the second row. In the third row, they are all zeros. So that's impossible we can make a leading one. So this is the reduced rational form of A. This is the reduced rational form of matrix A. If I call this matrix B, then matrix B can be obtained by performing a sequence of elementary row operations on matrix A. Then we say matrix A and B, they are row equivalent. So here, this matrix B can be obtained by performing a sequence of elementary row operations on A. Then we say matrices A and B, they are row equivalent. In this example, matrix B is obtained by performing a sequence of elementary row operations on A. So matrices A and B are row equivalent. Also, all matrices here are row equivalent. And they can be obtained from we can obtain one matrix from the others. All matrices here are row equivalent. In addition, all above matrices are row equivalent. All above matrices are row equivalent. We can obtain this one matrix from the other by doing some elementary row operations. So they are all equivalent matrices. They are all row equivalent. Next, let me introduce elementary matrix. If a matrix can be obtained by performing exactly one elementary row operation on identity matrix, then it's called an elementary matrix. If a matrix can be obtained by performing exactly one elementary row operation on identity matrix, then it's called an elementary matrix. Let me show you an example. For example, 1, 0, 0, 1. That's a 2 by 2 identity matrix. That's I2. If I perform one operation, for example, if I multiply first row by 5, I get 5, 0, 0, 1. This is called elementary matrix. This is called elementary matrix. It's obtained by performing exactly one elementary row operation on identity matrix. Another example, I3 is 1, 0, 0, 0, 1, 0, 0, 0, 1. That's a 3 by 3. That's a 3 by 3 identity matrix. If I interchange row 1 and row 3, I get 0, 0, 1, 0, 1, 0, 1, 0, 0. That's also an elementary matrix. It's obtained by performing exactly one row operation on identity matrix. This is also identity matrix. Another example, I4 is 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. For example, if I multiply row 2 by 5, add it to row 4. If I multiply row 2 by 5, add it to row 4, I get 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. Multiply row 2 by 5, add it to row 4, I get 0, 5, 0, 1. This is also identity matrix. This is also elementary matrix. It's obtained by performing exactly one elementary row operation on identity matrix. So those are examples of elementary matrix. They can be obtained by performing exactly one operation on identity matrix. And this elementary row operation here, they are called the corresponding elementary row operation to these elementary matrices. So in the above example, the operation 5 times row 1 is the corresponding elementary row operation of the matrix 5, 0, 0, 1. The operation interchange row 1, row 3. The operation interchange row 1, row 3 is the corresponding elementary row operation of the matrix 0, 0, 1, 0, 1, 0, 1, 0, 0, and the operation multiply row 2 by number 5 and then add it to row 4. This is the corresponding elementary row operation of this matrix 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 5, 0, 1. Those are some examples of elementary matrices. Next, Let's look at some examples. For each of the following matrices, determine whether it's an elementary matrix. Number 1, is this matrix elementary matrix? Is this an elementary matrix? Can we obtain this matrix by performing exactly one operation on the identity matrix? This is a 3 by 3 matrix. So the identity matrix is 1 0 0 0 1 0 0 0 1. Can we obtain this matrix from identity by performing exactly one operation? Can we obtain this matrix from identity matrix by performing exactly one elementary row operation? If we compare this matrix, we can see that the only difference in the second row we have 3 here. So all I can do is I can multiply row 2 by 3. In the identity matrix, I can multiply row 2 by 3. If I multiply row 2 by 3, I get this matrix. Since this matrix can be obtained by performing exactly one operation on identity matrix, this is an elementary matrix. So for number 1, the answer is yes. The corresponding operation is corresponding operation is I can multiply row 2 by 3. This is the corresponding operation. I can multiply row 2 by 3 to obtain this matrix. Number 2. Is this an elementary matrix? Is this an elementary matrix? This is a 2 by 2 matrix. Can we obtain this matrix by performing exactly one operation on identity matrix? This matrix 0 1 1 0. Can we obtain this matrix by performing exactly one operation? Here all I can do is I can interchange row 1 and row 2. If I interchange row 1 and row 2, I get this matrix. So by interchanging row 1 and row 2, I obtain this matrix. So since this matrix can be obtained by performing exactly one operation on the elementary matrix, this is on identity matrix. This is elementary matrix. Since this matrix can be obtained by performing exactly one operation on the identity matrix, then this is elementary matrix. So number 2, yes, it is elementary matrix. The corresponding operation to obtain this matrix is I interchange row 1 and row 2. Interchange row 1 and row 2 on identity matrix, I get this matrix. So this is the corresponding operation of this matrix, which is interchange row 1 and row 2. That's called a corresponding elementary row operation. Next, number 3. Is this an elementary matrix? This is a 4 by 4 matrix. 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1. This is a 4 by 4 identity matrix. Can we obtain this matrix? Can we obtain this matrix by doing exactly one operation? Can we obtain this matrix by doing exactly one operation on identity matrix? If we compare this matrix, we can see that the only difference is there's extra 2 here. There's extra 2 here. So all I can do is I can multiply row 1 by number 2 and then add it to row 3. So I can multiply row 1 by number 2, add it to row 3. So this is a corresponding operation. This is corresponding elementary row operation. By multiply first row by number 2 and add it to the third row, I got this matrix. So this is elementary matrix. So this is elementary matrix. The corresponding operation is I multiply row 1 by 2 and then add it to row 3. That's the corresponding operation. That's the corresponding operation to obtain this matrix. So the corresponding operation to obtain this matrix is I multiply row 1 by 2 and then add it to row 3. Next example, is this an elementary matrix? This is a 2 by 2 matrix. The 2 by 2 identity matrix is 1, 0, 0, 1. Can we obtain this matrix by doing exactly one row operation? Let's try. If I multiply first row by 3, add it to the second row. I get 1, 0, 3, 1, which is nonsense this. Or if I multiply second row by 2, add it to the first row. If I multiply second row by 2, add it to the first row. I get 0, 1, 1, 2. I don't get this matrix. So this matrix cannot be obtained by doing exactly one row operation from identity matrix. So this is not elementary matrix. This is not elementary matrix. This is not an elementary matrix. Number 5. Is this an elementary matrix? This is a 3 by 3 matrix. The 3 by 3 identity matrix is 1, 0, 0, 0, 1, 0, 0, 0, 1. Can we obtain this matrix by doing exactly one row operation? Can we obtain this matrix by doing exactly one row operation? If I interchange row 1 and row 3, I don't get this. If I interchange row 2 and row 3, I don't get this. So it looks like I take two operations. If I interchange row 1 and row 2, I get 0, 1, 0, 1, 0, 0, 0, 0, 1. If I interchange row 2 and row 3, I get 0, 1, 0, 0, 0, 1, 1, 0, 0, which is this matrix. If we take more than one row operation, this is not elementary matrix. Since we take more than one row operation, this is not elementary matrix. So no. This matrix cannot be obtained by doing exactly one row operation on identity matrix. So this is not elementary matrix. How about number 6? Is this elementary matrix? This is a 4 by 4 matrix. A 4 by 4 identity matrix is 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. This matrix here is 1, 0, 0, 0, 0, 2, 0, 0, 0, 0, 3, 0, 0, 0, 0, 4. Can we obtain this matrix by doing exactly one row operation? It looks like I need to multiply second row by 2, multiply the third row by 3, and multiply the fourth row by 4. It looks like it takes 3 operations here. It takes 3 operations. Multiply second row by 2, multiply third row by 3, multiply fourth row by 4. Since it takes more than one row operations, this is not elementary matrix. Since it takes more than one row operations, this is not elementary matrix. So no. This matrix cannot be obtained by using exactly one row operation on identity matrix. So this is not an elementary matrix. Next, how about number 7? Is this an elementary matrix? This is a 2 by 2 matrix. We know that the 2 by 2 identity matrix is 1, 0, 0, 1. And this matrix here is 1, 0, 0, 0. Can we obtain this matrix by doing one operation on identity matrix? If we compare the matrices, we can see that the only difference is this 0 here. This is a leading 1, this is a 0. It doesn't matter what operation we use, we can never make leading 1 to be 0. So this won't be elementary matrix. In general, if a matrix has a row of 0 or a column of 0, since we can never make leading 1 to be 0 by doing row operations, the matrix won't be identity matrix, won't be elementary matrix. So any matrix with a row of 0 or column of 0 won't be elementary matrix. Any matrix with a row of 0 or column of 0, it won't be elementary matrix. Now how about number 8? Number 8 itself is identity matrix. Number 8 itself is identity matrix. Is this elementary matrix? So we know that the 3 by 3 identity matrix is 1, 0, 0, 0, 1, 0, 0, 0, 1. And the matrix in number 8 is also an identity matrix. 1, 0, 0, 0, 1, 0, 0, 0, 1. Is this an elementary matrix? Can we obtain this by doing one operation on identity matrix? Here we can do many operations. For example, I can multiply first row by 1. That's an elementary row operation. If I multiply first row by 1, I get identity matrix. I get the same matrix again. Or I can multiply second row by 1. If I multiply second row by 1, I still get the same matrix. So this is elementary matrix. This is elementary matrix. So this is elementary matrix. In general, all identity matrices are elementary matrices. All identity matrices are elementary matrices. So for elementary matrices, keep the following idea in mind. First of all, an elementary matrix is always a square matrix. Because elementary matrix is obtained by doing one operation on identity matrix. Since identity matrices are square matrices, by doing one row operation, it won't change the dimension, it won't change the size of the matrix. So elementary matrix is always a square matrix. Next. A matrix with a row of 0 or a column of 0. It's not elementary matrix. A matrix with a row of zeros or a column of zeros is not elementary matrix. And also, identity matrix is always an elementary matrix. Identity matrix is always an elementary matrix. I can simply doing the operation by multiplying the first row by 1 or second row by 1. So identity matrix is always elementary matrix. Now here, someone may ask, why we need to learn elementary matrices? What's the point of learning elementary matrices? In order to see why it's important to learn elementary matrices, let's observe some examples. I'll explain to you why. In the previous example, we know that these three matrices, they are elementary matrices. Let me call this matrix E1, E2, E3. Let's observe this example first. Let E1 be the first elementary matrix 1 0 0 0 3 0 3 0 0 0 1. Let E2 be the elementary matrix 0 1 1 0. Let E3 be the elementary matrices 1 0 0 0 0 0 1 0 0 2 0 1 0 0 0 0 1. And their corresponding operations for E1 is 3 times row 2. For E2 is interchange row 1, row 2. For E3 is 2 times row 1 plus R3. They are elementary matrices. And their corresponding operations. They are corresponding elementary row operations. Their corresponding elementary row operations are 3 times row 2, 3 times row 2 for E1. Interchange row 1, row 2, that's for E2. And 2 times row 1 plus R3, that's for E3. Those are elementary, that's their corresponding elementary row operations of these three elementary matrices. Next, let matrix A, let A be a 3 by 3 matrix. 1, 2, 3, 4, 5, 6, 7, 8, 9. Let B be a 2 by 2 matrix. 1, 2, 3, 4. For matrix C, let's make it easier. Let C be a 4 by 2 matrix. 1, 2, 0, 6, 7, 1, 4, 0. The A, B, C beneath 3 matrices. Next, let's compute E1 times A, E2 times B, and E3 times C. Let's compute E1 times A first. What's E1 times A? E1 is a matrix 1, 0, 0, 0, 3, 0, 0, 0, 1. A is 1, 2, 3, 4, 5, 6, 7, 8, 9. If I multiply these two matrices, what do we get? When we multiply two matrices, we take row times column. Row times column, I get 1 here. Row times column, I get 2 here. Row times column, I get 3. In the second row, row times column, I get 0, 0, 3 times 4 is 12. Next, row times column, I get 0, 0, 3 times 4 is 15. Next, row times column, I get 0, 0, 6 times 3 is 18. Next, take row times column. I get 0 plus 0 plus 7. Next, row times column. I get 0 times 0 plus 8. Next, row times column. I get 0 times 0 times plus 9. If we observe these two matrices, if we compare E1A with matrix A, do you see any relationship between these two matrices? If you don't see it, it's okay. Let's compute E2B first. If we compute E2B, matrix E2 is 0, 1, 1, 0. Matrix B is 1, 2, 3, 4. Let's multiply the matrices. Take row times column. Row times column, I get 3. Next, row times column, I get 4. Row times column, I get 1. Row times column, I get 2. If we compare this matrix E2B with matrix B, do you see any relationship between these two matrices? If you don't see it, it's okay. Let's compute E3C first. What's E3C? E3 is the matrix 1, 0, 0, 0, 0, 1, 0, 0, 0, 2, 0, 1, 0, 0, 0, 0, 0, 1. 1, 0, 0, 0, 0, 1, 0, 0, 2, 1, 2, 0, 1, 0, 0, 0, 0, 1. That's E3. Matrix C is this 4 by 2 matrix. 1, 2, 0, 6, 7, 1, 4, 0. If we multiply these two matrices, use row times column. Row times column. I get 1 here. Next, row times column. I get 2 here. Next, row times column. I get 0. Next, row times column. I get 6. Next, row times column. 1 times 2 is 2. That's 0. 7 times 1 is 7. That's 0. So we got 2 plus 7, which is 9. Next, row times column. 2 times 2 is 4. That's 0. That's 1. That's 0. 4 plus 1 is 5. Next, row times column. I get 4. Next, row times column. I get 0. That's the matrix E3 times C. Now, let's compare the matrix. Compare matrix A and E1A. Do you see that relationship here? Matrix A is 1, 2, 3, 4, 5, 6, 7, 8, 9. E1A is 1, 2, 3, 12, 15, 18, 7, 8, 9. If we compare matrix B with E2B, what relationship do we see here? E2B is 3, 4, 1, 2. If we compare C with E3C, matrix C is 1, 2, 0, 6, 7, 1, 4, 0. E3C is 1, 2, 0, 6, 9, 5, 4, 0. Now, compare matrices A and E1A. It looks like the first row is exactly the same. Last row is exactly the same. If we try to obtain E1A from A, what operation can we make here to obtain E1A from matrix A? It looks like if I multiply second row by 3, I can make 12, 15, 18. It looks like if I multiply second row by 3, I can obtain E1A from A. If we observe B and E2B, for these two matrices, we can see that all entry looks the same. The only difference, row 1 and row 2 switched, which means in matrix B, if I interchange row 1 and row 2, I get E2B. In matrix B, if I interchange row 1 and row 2, I get E2B. Without doing matrix multiplication, I get E2B. Now observe matrix C and E3C. We can see that first row looks exactly the same. Second row looks exactly the same. And the last row looks exactly the same. The only difference is the third row. It looks like here, if I multiply first row by 2 and then add it to the third row, I can get this. If I multiply first row by 2 and add it to the third row, I can get this. If I multiply first row by 2, add to the third row, 2 times 1 is 2, 2 plus 7 is 9. 2 times 2 is 4, 4 plus 1 is 5. So if I do this operation, I can get E3C without actually multiplying the matrices. So here we can see that from A to E1A, I can do the operation, I can do the row operation 3 times row 2. From B to E2B, I can do the operation by interchanging row 1 and row 2. From C to E3, from C to E3C, I can do an operation multiply 2 to row 1 and add to row 3. If we observe this operation, with the corresponding operations of E1, E2, E3, we can see that they are exactly the same. 3 times R2, 3 times rho 2. That's a corresponding row operation of E1, which is this operation here. Interchanging row 1, row 2. That's a corresponding row operation of E2, which is exactly the same as this operation here. 2 times row 1 plus row 3. That's a corresponding row operation of E3, which is exactly the same as this row operation here. So, based on this calculation, what conclusion can we make? Based on the previous example, we have a following theorem called row operation by matrix multiplication. Let E be an elementary matrix, and let A be any matrix such that the product EA is well defined. Then EA can be obtained by performing the corresponding elementary row operation of E on A. If EA is defined, then EA can be obtained by performing the corresponding elementary row operation of E on A. In the previous example, E1 is an elementary matrix, and that's its corresponding elementary row operation. If I perform this operation on matrix A, I get matrix E1 times A. Similarly, E2 is another elementary matrix, and that's its corresponding elementary row operation. If I perform this operation on matrix B, I get a matrix E2 times D. E3 is another elementary matrix, and that's its corresponding elementary row operation. If I perform this operation on matrix C, I get a matrix E3 times C. So the product EA can always be obtained by performing the corresponding elementary row operation of E on A. And also be very, very careful. In the product EA here, the elementary matrix E must always be on the left side. In the product EA here, the elementary matrix E must always be on the left side. In the previous example, in the product E1A, E2B, E3C, the elementary matrices must always be on the left side. Otherwise, it won't work. If we put elementary matrices on the right side, it won't work. So this matrix multiplication, E1 times A, it can be done by performing a row operation on A. Conversely, this row operation on A can also be done by using matrix multiplication, E1 times A. That's what this theorem says. Row operation by matrix multiplication. In general, a row operation can be done by using matrix multiplication, and matrix multiplication can be done by using row operations. That's what this theorem says. Next, let's look at an example here. Let matrix A, B, C, D be these 4 matrices. Solve each of the following matrix equation for an elementary matrix E. Here on each equation, E is an unknown. We are solving the equation for each E here. Let's do part A first. Part A says E times A equal to B. We are solving an elementary matrix E. Since E is an elementary matrix, let's compare matrix A and matrix EA. Matrix A here is given as 1, 1, 1, 1 in the first row, 1, 2, 3, 4 in the second row, 0, 4, 0, 2 in the third row. What's matrix EA? In part A, we know that E times A is B. Matrix B is given as 1, 1, 1, 1 in the first row, 1, 2, 3, 4 in the second row, 0, 2, 0, 1 in the third row. Now, in order to solve for E, let's compare this matrix A and EA. What operation should we perform on A to get EA? What operation should we perform on A to get EA? Let's observe the matrices here. You can see that first row looks exactly the same. Second row looks exactly the same. In the third row, 4 become 2, 2 become 1. It looks like I divide the third row by 2 here. So, if I multiply the third row by half, this is an elementary row operation. If I perform this operation on A, I get a matrix EA. And the previous theorem says EA can always be obtained by performing the corresponding elementary row operation of E on A. EA can always be obtained by performing the corresponding elementary operation of E on A. So this operation is the corresponding elementary law operation of E. This operation here is the corresponding elementary operation of E. If I know the corresponding elementary operation of E, what's E here? So in order to get E, we start from identity matrix. In order to get E, I start from identity matrix. This matrix A here is three rows, 4 columns. It's a 3x4 matrix. Then what's the dimension of E? E must be a square matrix, and the column of matrix E must match the number in columns in matrix A. So in order to match the dimension, E must be a 3x3 matrix. So E must be a 3x3 matrix, since E must always be square matrix. Now, so I start from the 3x3 identity matrix. If I know the corresponding elementary operation of E, then what's E? E can be obtained by performing the same operation here. Since this is the corresponding elementary operation of E, E can be obtained by using the same operation here. So take half of R3. If I perform this operation here, take half times R3. I get 1, 0, 0, 0, 1, 0, 0, 0, half. This is matrix E. This is matrix E, and that's its corresponding elementary operation. This is matrix E. So in part A, E is 1, 0, 0, 0, 1, 0, 0, 0, half. So in this equation, in order to find E, we first of all observe operation from A to EA. We first of all observe operation from A to EA, then perform the same operation to an identity matrix and get E. First of all observe operation from A to EA, then apply the same operation to an identity matrix and get E. Now part B. Solve an equation EA equal to C. Let's compare matrix A and EA. Matrix A here is 1, 1, 1, 1 in the first row, 1, 2, 3, 4 in the second row, 0, 4, 0, 2 in the third row. What's matrix EA in part B? In part B, EA equal to C. So in part B, matrix EA is matrix C. Matrix C has 1, 2, 3, 4 in the first row, 1, 1, 1, 1 in the second row, 0, 4, 0, 2 in the third row. Now compare the matrix A and EA. What operations should I perform here to get EA? What operations should I perform on A to get EA? If we compare the matrices, we can see that the third row looks exactly the same, but the first row and the second row switched, which means the operation here is interchanging row 1 and row 2. This is an elementary row operation, so that's the corresponding elementary row operation of E. This is the corresponding elementary row operation of E. Then we perform the same operation to identity matrix. We perform the same operation to identity matrix. Since matrix A is a 3x4 matrix, it has 3 rows, 4 columns. The dimension in E must match this matrix. The number of columns in E must be the same as the number of rows in A. And since E must be a square matrix, E is a 3x3 matrix. Now, identity matrix here, we use 3x3 identity matrix. This is a 3x3 identity matrix. Perform the same operation. Perform the same operation here. This is the corresponding elementary row operation of E. Perform the same operation here. Interchange row 1 and row 2. I get 0, 1, 0, 1, 0, 0, 0, 0, 1. This is E. This is E. So here is 0, 1, 0, 1, 0, 0, 0, 0, 1. So in order to solve for E, we first of all observe an operation from A to EA. Once we find operation, this is the corresponding elementary row operation of E. Then perform the same operation to an identity matrix. We get E. It's part B. Part C. Solve an equation EA equal to D. So in order to solve for E, let's first of all compare matrix A and EA. Let's first of all compare matrix A and EA. Matrix A here is 1, 1, 1, 1 in the first row. 1, 2, 3, 4 in the second row. 0, 4, 0, 2 in the third row. Matrix EA. What's matrix EA? In part C, matrix EA is matrix D. Here, matrix D is 1, 1, 1, 1 in the first row. 1, 2, 3, 4 in the second row. And the first two rows stays the same. 1, 1, 1, 1. 1, 2, 3, 4. The third row looks very different. Third row is 3, 7, 3, 5. Let's compare this. Let's observe this matrix. What operation should I perform on A to obtain this matrix here? First row looks exactly the same. Second row looks exactly the same. If you observe, compare the third row here. We have 3, 7, 3, 5. It looks like I multiply first row by 3, add it to the third row. It looks like here I multiply first row by 3, add it to the third row. If I multiply first row by 3, add it to the third row, I get a matrix EA. So this must be the corresponding elementary row operation of E. Since EA can be obtained by performing this operation on A, this must be the corresponding elementary row operation of E by the previous theorem here. Once I know the corresponding elementary row operation of E, I can find E by performing the same operation on an identity matrix. Here, since A is 3 by 4 matrix, E must be a 3 by 3 matrix. So identity matrix starts from 3 by 3 identity matrix. 1, 0, 0, 0, 1, 0, 0, 0, 1. Now perform the same operation on identity matrix. 3 times row 1 plus row 3. 3 times row 1 plus row 3. I get 1, 0, 0, 0, 1, 0, 3, 0, 1. So this is elementary matrix E. So here E is 1, 0, 0, 0, 1, 0, 0, 0, 3, 0, 1. That's the solution for E. Now, how do we check the answer? How do we check the answer? How do we check the answer? If we want to check the answer, we take E times A, and we must get D. Let's check. If the answer is correct, when I take E times A, I must get D. Let's check. E times A, E is 1, 0, 0, 0, 1, 0, 3, 0, 1. Matrix A is 1, 1, 1, 1, 1, 2, 3, 4, 0, 4, 0, 2. Let's multiply. What do we get? When we multiply matrices, use row times column. row times column, I get 1 here. 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 Row times column, I get 1. Row times column, I get 2. Row times column, I get 3. Row times column, I get 4. Next, row times column, I get 3, 0, 0, which is 3. Row times column, I get 1 times 3 is 3. 4 times 1 is 4. 3 plus 4 is 7. Next, row times column. 1 times 3 is 3. That's 0, that's 0, I get 3. Next, row times column. I get 3, 0, 2. 3 plus 0 plus 2 is 5. That's exactly the same as D. That's exactly the same as D. That's how we check the answer. Next example. In the previous example, let matrix F be 1, 1, 1, 1, 0, 1, 2, 3, 0, 0, A, negative 10. Solve an equation. MA equal to F for M. In the previous example, let matrix F be 1, 1, 1, 1, 0, 1, 2, 3, 0, 0, negative 8, negative 10. Solve an equation MA equal to F for M. So, in order to solve for M, let's compare matrix A and MA. Let's compare matrix A and MA. In order to solve for M, let's compare matrix A and MA. What's matrix A here? Matrix A is the matrix 1, 1, 1, 1, 1, 2, 3, 4, 0, 4, 0, 2. Matrix MA here is MA equal to F. Matrix MA equal to F, which is 1, 1, 1, 1, 0, 1, 2, 3, 0, 0, negative A, negative 10. Now let's compare these two matrices. What operation should we perform on A to get this matrix? It may take multiple steps. What operation do we perform on A to get this matrix? If we compare this matrix, we can see that first row looks exactly the same. Second row becomes 0, 1, 2, 3. It looks like here I multiply first row by negative 1, add it to the second row. It looks like here I multiply first row by negative 1, add it to the second row. Let's try this operation here. I multiply first row by negative 1, add it to the second row. If I perform this operation, I get 1, 1, 1, 1, 0, 1, 2, 3, 0, 4, 0, 2. Now, let's compare these two matrices. Here, first row looks exactly the same. Second row looks exactly the same. Third row looks a little different. Here in MA, third row becomes 0 here. How do we get 0 here? What I can try is I can multiply second row by negative 4. Add it to the third row. Let's try. If I multiply second row by negative 4, add it to the third row. Negative 4 times 1 is negative 4. Negative 4 plus 4 is 0. Negative 4 times 2 is negative a. Negative a plus 0 is negative a. Negative 4 times 3 is negative 12. Negative 12 plus 2 is negative 10. So that's the right operation. Now, how do we find m here? Let's observe. This is an elementary operation. This is an elementary operation. Assume, let's call this to be assume this is the corresponding elementary operation assume this is a corresponding elementary operation of a matrix called E1. So E1 is elementary matrix, and this is the corresponding elementary operation of E1. That's another elementary operation. Let's assume this is the corresponding elementary operation of E2. Let's call this matrix E2. Here, these two operations, they are both elementary operations. Assume this is the corresponding elementary operation of matrix E1. Assume this is corresponding elementary operations of matrix E2. What's E1 and E2? How do we find E1 and E2? For E1 and E2, we perform the same operation to an identity matrix. For E1 and E2, we perform the same operation to an identity matrix. So start from identity matrix. 1, 0, 0, 0, 1, 0, 0, 0, 1. Perform the same operation to an identity matrix. Negative 1 times row 1 plus row 2. Negative 1 times row 1 plus row 2. Negative 1 times row 1 plus row 2. What do I get here? I get first row stays the same. Multiply negative 1 to row 1. Add it to row 2, I get negative 1, 1, 0. Third row stays the same. This is E1. Performing the same operation to an identity matrix, what we get is E1. So here, E1 is the matrix 1, 0, 0, negative 1, 1, 0, 0, 0, 1. How about E2? Perform the same operation to identity matrix, we get E2. This is a corresponding elementary operation of E2. Perform the same operation to identity matrix. So start over. Don't start from here, start over. Write identity matrix again. 1, 0, 0, 0, 1, 0, 0, 0, 1. Start over. Write identity matrix again. Then perform the same operation. Negative 4 times row 2 plus row 3. Now perform this operation on identity matrix. What do we get here? First row stays the same. Second row stays the same. On the third row, multiply negative 4 to row 2. Add it to row 3. I get 0, negative 4, 1. This is elementary matrix E2. This is elementary matrix E2. 1, 0, 0, 0, 1, 0, 0, negative 4, 1. That's the elementary matrix E2. Now, how do we find M based on E1, E2? Here, since this is a corresponding elementary operation of E1, which means if I take E1 times A, I get this matrix. If I take E1 times A, I get this matrix. The elementary matrix E1 must come first. If I take E1 times A, I get this matrix. And again, since this operation here is a corresponding operation of E2, that means if I take E2 times this matrix, I get MA. If I take E2 times this matrix, I get this matrix here, MA. And this is E1 times A. If I take E2 times this matrix, I get this matrix MA. And by associative law, this matrix can be rewritten as E2 times E1 times A equal to MA. Then, by matching here, we can see that matrix M is E2 times E1. By matching the matrix, we can see that matrix M is E2 times E1. So matrix M equal to E2 times E1 by matching. By matching here, we can see that M is E2 times E1. E2 here is 1, 0, 0, 0, 1, 0, 0, negative 4, 1. E1 is 1, 0, 0, negative 1, 1, 0, 0, 0, 1. Then multiply, use row times column. Row times column, I get 1 here. Row times column, I get 0. Row times column, I get 0. Row times column, I get negative 1 here. Row times column, I get 1. Row times column, I get 0. Next, row times column. Row times column, I get positive 4. Next, row times column, I get negative 4. Next, row times column, I get positive 1. So this is matrix M. That's how we solve for M. This is matrix M. Now, how do we check the answer? How do we check the answer? If we want to check the answer, we take M times A, we must get F. Let's check the answer. If we take M times A, we must get F. Let's check. M times A. M is matrix 1, 0, 0, negative 1, 1, 0, 4, negative 4, 1. Matrix A is 1, 1, 1, 1, 1, 2, 3, 4, 0, 4, 0, 2. Let's multiply. Row times column. Row times column, I get 1. 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 Next, row times column. Row times column, negative 1 plus 1 plus 0 is 0. Row times column, negative 1 plus 2 plus 0. Negative 1 plus 2 plus 0 is 1. Next, row times column, negative 1 plus 3 plus 0 is 2. Next, row times column, negative 1 plus 4 plus 0 is positive 3. Next, row times column, 4 plus negative 4 is 0. Next, row times column, 4 plus negative A. 4 plus negative A plus 4 is 0. Next, row times column, 4 plus negative 12 plus 0. 4 plus negative 12 is negative A. Next, row times column, 4 plus negative 16 plus 2. 4 plus negative 16 is negative 12. Negative 12 plus 2 is negative 10. That's exactly the same as matrix F. That's exactly the same as matrix F. So that's how we check the answer. M times A equal to F. That's the answer. Next, let me introduce the inverse operations of the elementary row operations. We know that there are 3 elementary row operations. We can multiply a row by a non-zero constant. We can interchange 2 rows. Or we can multiply a row by a constant added to another row. Those are the 3 elementary row operations. Next, we try to find the inverse operation. What are their inverse operations? Let's think of this. Think of a matrix. Let's make it simple. 1, 1, 1. 1, 2, 3, 0, 0, 1. Make it simple. Let's try to perform the first operation. For example, if I multiply first row by 3, for example, I get 1, I get 3, 3, 3, 1, 2, 3, 0, 0, 1. Now, based on this matrix here, how do I go back? How do I go back from this matrix to this? What operation should I use to go from this matrix back to this matrix? That's the inverse operation. What operation should we use here? If we should go this way, I can divide the first row by 3 to go back. If I divide the first row by 3, I can go back here. So, divide by 3 means multiply by 1/3. If I multiply first row by 1/3, I go back to this. So you can see that my opposite operation of 3 times row 1 is 1/3 times row 1. So in general, for an operation k times row I, the inverse operation is we take the reciprocal 1 over k times row I. If I multiply row I by k and then multiply by 1 over k, I go back to the original matrix. So this is the inverse operation of this operation here. Next, if I interchange two rows, what's the inverse operation? If I interchange two rows, what's the inverse operation? Think of this matrix. 1, 1, 1, 1, 2, 3, 0, 0, 1. If I interchange two rows, say I interchange row 2 and row 3, here we get 1, 1, 1 in the first row, 0, 0, 1 in the second row, and 1, 2, 3 in the third row. If we should go backward, what operation should we use? If we should go backward, we can interchange row 2 and row 3 again. If we interchange row 2 and row 3 again, it goes back to the original matrix. So that's the inverse operation of this. They are exactly the same. So for this operation, if I interchange row I and row J, the inverse operation is I change it again. I change row I and row J again, it goes back to the original matrix. So for this elementary operation, the inverse operation is exactly the same. Interchange row I and row J again one more time. I go back to the original matrix. Next operation, I can multiply a row by a constant k and then add it to a different row. What's its inverse operation? Let's look at an example. Use the same matrix. 1, 1, 1, 1, 2, 3, 0, 0, 1. If I multiply a row by a constant and add it to a different row, think of this. If I multiply first row by 2, add it to the third row, what do I get? I get 1, 1, 1 in the first row, 1, 2, 3 in the second row. I get 2, 2, 3 in the third row. Now, if we should go backward, what operation should we use? If we should go backward, what operation should we use? First row stays the same, second row stays the same. We try to make 0 here, make 0 here. So what I can do is, if we should go backward, what I can do is I can multiply first row by -2, add it to the third row. Multiply first row by -2, add it to the third row. I get 0, 0, and 1. So the opposite operation of 2 times row 1 plus row 3 is -2 times row 1 plus row 3. So in general, when we have k times row 1 plus row 1, k times row I plus row j, when we have k times row I plus row j, the opposite operation is I take -k times row I, then plus row j. take negative k times row I plus row j. That's an opposite operation of this. Those are inverse operation. Those are inverse operation of these three elementary row operations. Note, the inverse operations of the elementary row operations they are also elementary row operations. The inverse operation of an elementary row operation, they are also elementary row operations. For example, for the first inverse operation, as long as k is not 0, 1 over k is not 0. If I multiply a row by a non-zero constant, that's an elementary row operation. And the second inverse operation is exactly the same as this elementary row operation. So this is an elementary row operation. The third operation here, the third inverse operation here, since k is a constant, negative k is another constant. Here we have a constant times a row plus another row. That's another elementary row operation. So they are all elementary row operations. A constant times a row, it interchanges two rows. A constant times a row added to another row. They are all elementary row operations. Next, let me show you a theorem. It says every elementary matrix is invertible, and its inverse matrix is also an elementary matrix. Let's prove it. Let E1 be an elementary matrix. I'm trying to prove E1 is invertible and it has an inverse matrix. Let lowercase e1 be the corresponding elementary row operation of E1, of capital E1. Let lowercase e1 be the corresponding elementary row operation of capital E1. Let E2 be the inverse operation of E1. Let E2 be the inverse operation of E1. Let lowercase e2 be the inverse operation of E1. Then we know that E2 is also an elementary row operation. E2 is also an elementary row operation. Here, lowercase e2 is an elementary row operation. If I perform this row operation on identity matrix, I will obtain an elementary matrix. Let's call this elementary matrix capital E2. Then capital E2 will be the corresponding elementary matrix of lowercase e2. So let capital E2 be the corresponding elementary matrix of E2, of small e2. Then think of this. What's E2 times E1 times I? What's E2 times E1 times I? E1 times I means I perform operation E1 on identity matrix. And then E2 times this matrix means I perform operation small e2 on this matrix. If I perform E1 first, then perform E2, they are opposite operations. I go back to identity. In identity matrix, if I perform operation E1 first and then perform its opposite operation, I go back to identity. And similarly, if I perform E2 first and then perform E1, I still go back to identity. If I perform E2 on identity matrix, then perform its inverse operation, I go back to identity. So E2 times E1 equal to identity, and E1 times E2 equal to identity, which means E1 and E2, they are inverse of each other. This matrix E1 and E2, they are inverse of each other, inverse matrix of each other. They are inverse matrices of each other. Hence, I can say E2 is the inverse of E1. And E2 is an elementary matrix. That complete the proof. Next, let me show you some equivalent statements. Let A be an n by n matrix. Then the following statements are equivalent. Equivalent means they are either all true or they are all false. If one of them is true, then they are all true. If one of them is false, then they are all false. The first statement says A is invertible. Second statement says A is equal to 0 has only trivial solution. Trivial solution means the only solution is OS equal to 0. The third statement says the reduced row echelon form of A is an identity matrix. The fourth statement says matrix A can be expressed as a product of elementary matrices. Let's prove their equivalent. In order to show these four statements are equivalent, we try to prove that if 1 is true, then 2 is true. If 2 is true, then 3 is true. If 3 is true, then 4 is true. And if 4 is true, then 1 is true. That's how we show that these four statements are equivalent. If one of them is false, the rest must be false. If one of them is true, the rest must be true. Everything must be true. So let's prove it. Let's first of all prove 1 implies 2. That means we assume 1, proof for 2. We assume 1, then proof for 2. So assume A is invertible. We try to prove that this equation A is equal to 0 has only trivial solutions. Assume A is invertible. Then what does it tell us? Then inverse of A exists. And inverse of A times A equal to identity. A times inverse A is also identity. That's what we have here. We try to prove in the second statement that AS equal to 0 has only trivial solution. This equation, AS equal to 0, if I multiply both sides by inverse of A, I have inverse of A times AX equal to A times 0. This is a zero matrix. This is a zero column matrix. This 0 is a zero column matrix. And then by associative law, left side can be rewritten as inverse of A times X. On the right side, any matrix times a zero column matrix is a zero column matrix. Any matrix times a zero column matrix is a zero column matrix. On the left side here, inverse of A times A is identity matrix. Identity matrix times X is X. So I get X equal to 0. That means in this column, S1, S2, up to Xn equal to a column of zeros, which means OX must be 0. Since the only solution is 0 for OX, then this is called trivial solution. So the equation AS equal to 0 has only trivial solution. Which means the only solution is 0. It has only trivial solution, means the only solution is 0. Next, we try to prove 2 implies 3. That means we assume statement 2 is true. We try to prove that statement 3 is also true. When we prove 2 implies 3, we cannot use any information from statement 1 and statement 4. We only allowed to use statement 2 to prove statement 3. We can't use anything from statement 1 and 4. So let's assume statement 2, proof for statement 3. Assume the equation AS equal to 0 has only trivial solutions. That means the only solution is S1 equal to 0, S2 equal to 0, Sn equal to 0. Assume this equation has only trivial solutions. Let A be the matrix A11, A12, up to A1n. A21, A22, up to A2n. Last row is AN1, AN2, up to ANN. Let A be this matrix. Then the augmented matrix of A. The augmented matrix of this equation AS equal to 0 can be written as matrix A followed by a column of 0. The augmented matrix AS equal to 0 can be written as matrix A followed by a column of 0, which looks like this. A11, A12 up to A1n. The last entry is 0. A21, A22, A2n. The last entry is 0. And on the last row, we have AN1, AN2, ANN. Last entry is 0. That's the augmented matrix of this equation, AS equal to 0. Next, we reduce the augmented matrix to the reduced row echelon form. Reduce the augmented matrix A followed by a column of 0 to the reduced row echelon form. Since this equation AS equal to 0 has only trivial solutions, then we know that S1 equal to 0, S2 equal to 0, and Sn equal to 0. OX are 0. It has only trivial solution. OX are 0. So, in the reduced row echelon form, we have in the first column, the coefficient of S1 in the first row, coefficient of S1 is 1. Coefficient of the rest must be 0. And it must equal to 0 here. In the second row, coefficient of S2 is 1, and coefficient of the rest must be 0. So S1 equals 0. That means S1 equals 0. S2 equals 0. And continue, we have 1s in diagonal. In the last row, coefficient of Sn is 1, and coefficient of the rest is 0. And they equal to 0. So, the reduced row echelon form of this matrix A followed by a column of 0 is in the form of IN. This is identity matrix with n rows and n columns. It's IN followed by a column of 0. So the reduced row echelon form of A0 equal to IN0. Therefore, the reduced row echelon form of A is IN. Therefore, if we ignore the column of 0, the reduced row echelon form of A is IN. That's a proof that 2 implies 3. Next, we shall prove 3 implies 4, which says if the reduced row echelon form of A is IN, then A can be expressed as a product of elementary matrices. Next, let's prove 3 implies 4. That means we assume 3 proof for 4. When we prove 3 implies 4, we cannot use any statement from 1 and 2. We cannot use any information from 1 and 2. So assume the reduced rational form of A is In. We try to prove that A can be expressed as a product of elementary matrices. If reduced rational form of A is In, that means by performing a sequence of elementary operations on A, by performing a sequence of elementary operations on A, In is eventually obtained. Let E1, E2, EK let E1, E2, EK, lowercase E1, E2, EK be this sequence of elementary operations. Let E1, E2, EK be this sequence of elementary operations. Which means I start from matrix A by performing this operation, no operation, E1, E2, E3, E1, E2, E3, eventually En, Ek, I obtain In. That's what it says here. Next, let capital E1, E2, Ek be their corresponding elementary matrices. Respectively. Next, when I perform operation E1 on A, I get a new matrix here. This new matrix can be found by using matrix multiplication, which is E1 times A, always with an elementary matrix on the left side. Always with an elementary matrix on the left side. So here I got a new matrix, E1 times A. Next, when I perform operation E2 on this matrix, I got another new matrix here. This new matrix can be obtained by using matrix multiplication, which is capital E2 times this matrix. So I get capital E2 times this new matrix. Always put elementary matrix on the left side. So this matrix here is E2 times E1 times A. There's a new matrix here. Next, when I perform the third operation, E3 on this matrix, I got a new matrix by using E3 times this new matrix. Always put an elementary matrix on the left side. So here I got a new matrix when I perform E3. Next, E3, E2, E1, and A. Continue. Eventually, when I perform operation EK, I got a new matrix by using EK times this matrix. Always put elementary matrix EK on the left side. After I perform EK on the matrix, I got I, identity matrix. After I perform operation EK, I got identity matrix. So this matrix, this product, equals to identity matrix IN. Next, we have to show A can be written as a product of elementary matrices. How do I get A by itself? Here? Since E1, E2, EK, they are elementary matrices. Then we know that all elementary matrices are invertible, and their inverse matrices are also elementary matrices. Since E1, E2, EK are elementary matrices, then they are all divisible. They are all invertible. Since they are all elementary matrices, they are all invertible. Let inverse E1, inverse E2, inverse EK be their inverses. And we know that they are all invertible. They are all elementary matrices. The inverse of elementary matrices are also elementary matrices. They are all elementary matrices. Now we can try to get A by itself. How do I get A by itself? EK, the second last one is E sub K minus 1. E3, E2, E1 times A equal to IN. I can first of all multiply both sides by EK, by inverse of EK. I can first of all multiply both sides by inverse of EK. Multiply both sides by inverse of EK. And then on the left side here, inverse of EK cancels EK. What's left is E sub K minus 1, E2, E1A, inverse of EK, times identity is inverse of EK. Next, I can multiply both sides by inverse of E sub K minus 1. Multiply both sides by inverse of E sub K minus 1. Then on the left side, inverse E sub K minus 1 cancels E sub K minus 1. What's left is E sub K minus 2, E2, E1A, On the right side, I get E sub k minus 1 inverse times E sub k inverse. By doing the same procedure, on the right side, I eventually will have E sub k minus 1 inverse, E sub k inverse, E sub k minus 1 inverse, E sub k minus 2 inverse. The index goes down. Eventually we'll have E2 inverse, E1 inverse. On the left side, eventually all this can cancel. E sub k minus 2, E2, E1 all can cancel. What's left is letter A. So matrix A can be written as a product of these matrices. And we know that they are all elementary matrices. Hence here, A can be written as a product of elementary matrices. That's 3 implies 4. That's a proof. 3 implies 4. Next, we need to prove 4 implies 1. We assume statement number 4. Prove statement number 1. Next, try to prove 4 implies 1. We assume A can be expressed as part of elementary matrices. We try to prove A is invertible. So assume A can be written as a product of elementary matrices. I'm trying to prove A is invertible. So let A equal to E1 times E2 times EK. Let A be written as a product of elementary matrices, where E1, E2, EK are elementary matrices. Since elementary matrices are all invertible, then we can say that E1, E2, EK are all invertible matrices, are all invertible. And from last class, we know that the product of invertible matrix is invertible. Since A is a product of invertible matrices, A is a product of invertible matrices, by the theorem we learned from last class, the product of invertible matrices is invertible. Then we can say A is invertible. The product of invertible matrix is invertible. Then we say A is invertible. Let's complete the proof that 4 implies 1. Since 1 implies 2, 2 implies 3, 3 implies 4, 4 implies 1. That means these 4 statements, they're all equivalent. If one of them is true, then they're all true. If one of them is false, they're all false. Next, let's look at example. Let A be the matrix 3, 4, 2, 1. Determine whether A is invertible. If A is invertible, whether A is a product of elementary matrices. So let's first of all determine whether A is invertible. How can we determine A is invertible or not? Here we can try to use equivalent statements. If one of these statements is true, then A is invertible. If one of the statements is false, then A is not invertible. So let's try to use the third statement to show A is invertible or not. If the reduced rational form of A is identity, then A is invertible. If the reduced rational form of A is not identity, then A is not invertible. So let's try to reduce the matrices. Here A is a matrix 3, 4, 2, 1. How can we reduce the matrix here? First of all, I try to make 1 in the first entry here. I don't want fractions. So what I can do is I can multiply second row by -1, add it to the first row. So second row stays the same. I get 1 and 3. Well, now I have a 1 here. This is a leading one. I try to make all entries below leading one to be 0. So what I can do here is I can multiply first row by -2, add it to the second row. First row here stays the same. Second row, I get 0. -2 times 3 is -6. -6 plus 1 is -5. Next, in the second row, I try to make the first non-zero entry to be 1. What I can do here is I can divide second row by -5, which means multiply by -1/5. Multiply second row by -1/5. I get 0, 1. First row stays the same. Next, I can multiply the second row by -3, add it to the first row. I get 1, 0, 0, 1. That's the reduced rational form of this matrix A. This is I2. Since the reduced rational form of A is identity matrix, by equivalence theorem, A is invertible. By equivalent statements, A is invertible. Next question. If A is invertible, write A as a product of elementary matrices. If A is invertible, write A as a product of elementary matrices. Here, what should we do? How can we write A as a product of elementary matrices? When we are doing proof for equivalent statements, for 3 implies 4, we try to show that A is a product of elementary matrices. What we did here is we first of all find operation E1, E2, E3, Ek to reduce A to identity matrix. Then let capital E1, E2, Ek be the corresponding elementary matrices of lowercase e1, e2, ek. Then eventually A can be written as a product of inverse of e1, inverse of e2, until inverse of ek. And since e1, e2, ek, they are elementary matrices, all their inverse matrices are also elementary matrices. So then I write A as product of elementary matrices. That's the procedure. So first step, find operation e1, e2, ek. In this matrix here, in this problem here, I reduce A to I2. This is the first operation called E1. This is my first operation, called this operation E1. This is my second operation. Let me call this operation E2. This is my third operation. Let me call this operation E3. This is my fourth operation. Let me call this operation E4. We know that A equal to inverse of E1 times inverse of E2 times inverse of EK. So let's find the inverse of these elementary matrices. How do we find the inverse of these elementary matrices? First of all, we try to find the inverse operation first. E1 is -1 times row 2 plus row 1. What's its inverse operation? For its inverse operation, we take -1 times R2 plus row 1. That's the rule for inverse operation of these three elementary row operations. When we have a constant times a row plus another row, I take negation of the constant times a row plus another row plus another row. So I take -1 times row 2 plus row 1, which is row 2 plus row 1. That's the inverse operation of E1. Operation of E2 is -2 times row 1 plus row 2, which means I negate the coefficient. I have -2 times row 1 plus row 2. That's the opposite operation of E2, which is 2 row 1 plus row 2. Next, for E3, operation of E3, it's -1/5 times row 2. -1/5 times row 2. How do we find the inverse operation? When we have a constant times a row, its inverse operation is the reciprocal of the constant times the same row. The reciprocal of the constant times the same row. So the reciprocal of -1/5 is -5 times the same row. That's the inverse operation of E3. Next, E4. E4 is operation -3 times row 2 plus row 1. When we have a constant times a row plus another row, its inverse operation is -3 times row 2 plus row 1, which is 3 row 2 plus row 1. Next, we try to find inverse of E1, E2, E3, E4 based on the inverse operation here. So start from identity matrix. This is 2 by 2 matrix, 1, 0, 0, 1. Perform the inverse operation, row 2 plus row 1. If I add row 2 to row 1, I get 1, 1, 0, 1. Add row 2 to row 1. This is inverse of E1. This is inverse of E1. Next, find inverse of E2. Again, start from identity matrix, 1, 0, 0, 1. Perform the inverse operation, 2 times row 1 plus row 2. 2 times row 1 plus row 2, so row 1 stays the same. 2 times row 1 plus row 2, I get 2, 1. This is inverse of E2. This is inverse of E2. Next, find inverse of E3. Start from identity matrix, 1, 0, 0, 1. Perform the inverse operation. We multiply -5 to row 2. Multiply -5 to row 2. I get 1, 0, 0, -5. That's inverse of E3. Next, find inverse of E4. Start from identity matrix. Start from identity matrix. Perform the inverse operation on identity matrix. We get 3 times row 2 plus row 1. 3 times row 2 plus row 1. Row 2 stays the same. 3 times row 2 plus row 1. I get 1, 3. That's inverse of E4. That's inverse of E1, E2, E3, E4. Next, A can be written as product of, let me copy E1, E2, E3, E4 here first. Inverse of E1 is the matrix 1, 1, 0, 1. Inverse of E2 is the matrix 1, 0, 2, 1. Inverse of E3 is the matrix 1, 0, 0, negative 5. Inverse of row 4 is 1, 3, 0, 1. So A is the product of inverse of E1 times inverse of E2 times inverse of E3 times inverse of E4. Let's check. If we multiply out, we should get A. Let's check. Inverse of E1 is 1, 1, 0, 1. Inverse of E2 is 1, 0, 2, 1. Inverse of E3 is 1, 0, 0, negative 5. Inverse of E4 is 1, 3, 0, 1. Let's multiply out. If I multiply first two matrices, what do I get? Use row times column. Row times column. 1 plus 2 is 3. Row times column. I got 0 plus 1 is 1. Next, row times column. 0 plus 2 is 2. Row times column. 0 plus 1 is 1. Next, multiply these two matrices. Take row times column. Row times column is 1. Row times column is 3. Row times column is 0. Row times column, I get negative 5. Next, multiply these two matrices. Take row times column. Row times column, I get 3. Row times column. 3 times 3 is 9. Negative 5 times 1 is negative 5. 9 plus negative 5 is 4. Next, row times column. I get 2 plus 0, which is 2. Next, row times column. I get 6 plus negative 5, which is positive 1. So here I write A is a product of elementary matrices. Next, let me show you a method to find inverse matrix. We call it if the reduced rational form of A is identity matrix, then that means if I perform a sequence of elementary row operations, E1, E2, until EK, I can obtain identity matrix IN. Then let E1, E2, the capital E1, E2, EK be the corresponding elementary matrices of E1, E2, EK. E1, E2, EK, respectively. Then when I perform operation E1 on A, I get E1 times A. When I perform operation E2 on a new matrix, I get E2 times the new matrix. Continue. When I perform operation EK on this matrix, I get EK times the resulting matrix. This is equal to identity matrix, IN. Here, since the reduced rational form of A is identity matrix, then by equivalent statements, A is invertible. So I can multiply both sides by inverse of A. If I multiply both sides by inverse of A, I get EK times E2 times E1 times A times inverse of A. On the right side, I get IN times inverse of A. On the left side, A and inverse of A can cancel. We get EK times E2 times E1 on the left side. On the right side, I get inverse of A by itself. Then next, if I multiply both sides by identity matrix, what do I get? If I multiply both sides by identity matrix, on the left side, let me leave it the same. I get EK times E2 times E1 times IN. On the right side, inverse of A times identity matrix is inverse of A, which means inverse of A equal to this expression. What does this expression mean? This expression here, E1 times IN, means I perform operation E1 on I. E2 times this matrix means I perform operation E2 on the resulting matrix, and so on. EK times this matrix means I perform operation EK of this resulting matrix. This expression says when we perform a sequence of elementary row operations to reduce A to an identity matrix, if we perform the same operation on the identity matrix, we will obtain inverse of A. This is called the inversion algorithm. Inversion algorithm says if the reduced rational form of A is identity, then by equivalent statement we know that A is invertible. The inverse of A exists. Next, perform a sequence of elementary row operations and reduce A to the identity matrix. Then if we perform the same operation on the identity matrix IN, we can obtain the inverse matrix A. We can obtain inverse matrix of A. If we perform the same operation on IN, we can obtain inverse matrix A. We can obtain inverse matrix of A. This is called inversion algorithm. Next, let's try an example using the same example here. Let matrix A equal to the matrix 3, 4, 2, 1. In the previous example, matrix A is 3, 4, 2, 1 for the inverse matrix. So, first step, perform a sequence of elementary row operations. Reduce A into identity matrix. So, perform a sequence of row operations reduce A to an identity matrix. That's what we did here. So that's the first operation, that's the second operation, that's the third operation, that's the fourth operation. So write down these four operations. Next, you try to perform the same operation on identity matrix. Perform the same operation on identity matrix. So we start from identity matrix. Identity matrix is 1, 0, 0, 1. Perform exactly the same operation. Let's perform E1. Perform exactly the same operation. E1 is -1 times row 2 plus row 1. Perform the same operation on identity matrix. We can get inverse matrix of A. That's E1, which means I multiply row 2 by negative 1 added to row 1. Row 2 here stays the same. Added to row 1, I get 1, -1 here. That's operation E1. Next, perform operation E2. Exactly the same operation. Multiply -2 to the first row, add it to the second row. Multiply -2 to the first row, add it to the second row. Here I get -2. -2 times -1 is +2. +2 plus 1 is +3. Next operation. Multiply row 2 by 1/5. -1/5. Multiply row 2 by -1/5. Multiply row 2 by -1/5. First row stays the same. I get 2 over 5 and -3 over 5. Next operation, multiply -3 to row 2, add it to row 1. Multiply -3 to row 2, add it to row 1. So row 2 stays the same. -3 times 2 is -6. -6 over 5 plus 1 is -1/5. -3 times -3 is +9. 9 over 5 plus -1 is 4 over 5. Second row stays the same. When I reduce A to identity, if I perform the same operation on identity, what I have here is the inverse matrix. Now, how can we check the answer? Last class we know that for matrix A, B, C, D, its inverse is 1 over, for 2 by 2 matrix, its inverse is 1 over AD minus BC. Then we interchange the main diagonal. I get DA. Change the sign for BC. I get -B, -C. Let's apply the old formula to this matrix. See what we get. If I apply the old formula to this matrix, inverse of A is 1 over AD minus BC, which is 3 minus A. Interchange A and D. Then change the sign for B and C. I get -4, -2. 1 over 3 minus A is -1/5. If I distribute -1/5 I get negative 1/5, 4/5, 2/5, and negative 3/5. That's exactly the same as what we have here. So that's the new technique of finding inverse matrix, which means I first of all reduce A to identity matrix, then perform the same operation on identity matrix. What I get here is inverse matrix. In general, we can do two things in one step. To make it easier, we can do two things in one step. In general, we can do two things in one step. For example, in this example, I first of all put the matrix A here, and then put the identity matrix next to A. So I have 3, 4, 2, 1. Identity matrix is 1, 0, 0, 1. Since I have to reduce matrix A and I using exactly the same operations, so I can do two matrices at the same time. I write two matrices together. That's matrix A, that's matrix I. Put it together. Then reduce two matrices at the same time. First of all, in the first row, I try to make leading one here. In order to avoid fractions, I can multiply second row by negative 1 and add it to the first row. So second row stays the same. I get 2, 1, 0, 1. Multiply second row by negative 1, add it to the first row. I get 1, 3, 1, negative 1. So I get 1, 3, 2, 1. That's exactly what we have here. 1, 3, 2, 1. Here is 1, negative 1, 0, 1. That's what we have here. 1, negative 1, 0, 1. We do two operations in one step. Next, I try to make 0 here. So I can multiply first row by negative 2. Add it to the second row. First row stays the same. 1, 3, 1, negative 1. Multiply first row by negative 2, add it to the second row. I get 0. Negative 2 times 3 is negative 6. Negative 6 plus 1 is negative 5. Negative 2 times 1 is negative 2. Negative 2 plus 0 is negative 2. Negative 2 times 1 is 2. 2 plus 1 is 3. So what we have here is, in matrix A is 1, 3, 0, negative 5. That's exactly what we have here. In matrix I, we get 1, negative 1, negative 2, and 3. That's what we have here. 1, negative 1, negative 2, positive 3. Next, in the second row, I try to make leading 1 here. So I can multiply second row by negative 1/5. Multiply second row by negative 1/5. First row stays the same. I get 1, 3, 1, negative 1. Multiply second row by negative 1/5. I get 0, 1, 2/5, and negative 3/5. In matrix A, we have 1, 3, 0, 1. That's exactly what we have here. In matrix I, we get 1, negative 1, 2/5, negative 3/5. That's exactly what we have here. So we are doing two matrices at the same time. Next, I can multiply second row by negative 3, add it to the first row. So second row stays the same. I get 0, 1, 2/5, negative 3/5. Multiply negative 3 to the second row, add it to the first row. So 1 stays the same. Negative 3 times 1 is negative 3. Negative 3 plus 3 is 0. Negative 3 times 2 is negative 6. Negative 6/5 plus 1 is negative 1/5. Negative 3 times negative 3/5 is positive 9/5. Positive 9/5 minus 1 is positive 4/5. So in matrix A, I eventually got identity here. This is identity. In matrix I get negative 1/5, 4/5, 2/5, negative 3/5. Here we have negative 1/5, 4/5, 2/5, negative 3/5. That's exactly what we have here. So the answer here, this is identity matrix. This is inverse of A. So in general, in order to find inverse matrix, we run a matrix first, then followed by identity matrix. Once I reduce this matrix to identity matrix, what we have here is an inverse matrix. So when I reduce matrix A to an identity matrix, the matrix I becomes inverse matrix of A. So that's the inversion algorithm. Next example, let A and B be two matrices. Find inverse of A and inverse of B if possible. Let's try to find inverse of A first. For inverse of A, we first of all write matrix A and identity matrix together. Here, matrix A is 3 by 3. Identity matrix is 1, 0, 0, 0, 1, 0, 0, 0, 1. Then try to reduce matrix A to identity matrix. What can we do here? In the first row, I try to have a leading 1 here. So all I can do is I can interchange row 1 and row 3. I get 1, 1, 1. 0, 0, 1. Second row stays the same. Third row stays the same. So it's first row and the third row. Next, this is a leading 1. Try to make all entries below leading 1 to be 0. Here, what I can do is I can multiply first row by negative 2, add it to the second row. So first row stays the same. 1 times negative 2 is negative 2. Negative 2 plus 2 is 0. Negative 2 times 1 is negative 2. Negative 2 plus negative 1 is negative 3. Negative 2 times 1 is negative 2. Negative 2 plus 0 is negative 2. That's 0, that's 1. Negative 2 times 1 is negative 2. Negative 2 plus 0 is negative 2. Next, I can multiply first row by negative 4, add it to the third row. Here I get 0. Negative 4 plus 0 is negative 4. Negative 4 plus 1 is negative 3. That's 1. That's 0. Negative 4 plus 0 is negative 4. Next, in the second row, in the second column, try to make leading 1 here. What can we do here? I try to avoid fractions. So what I can do is I can multiply third row by negative 1, add it to the second row. Multiply third row by negative 1, add it to the second row. First row stays the same. 1, 1, 1. 0, 0, 1. Third row stays the same. 0, negative 4, negative 3, 1, 0, negative 4. Multiply third row by negative 1, add it to the second row. I get 0, 1, 1. Negative 1, 1. Here I got 4. 4 plus negative 2 is 2. Next, this is a leading 1. We try to make an entry above 1 to be 0, and an entry below 1 to be 0. What I can do is I can multiply second row by negative 1, add it to the first row. So second row here stays the same. I get 0, 1, 1. Negative 1, 1, 2. Multiply second row by negative 1, add it to the first row. get 0, 1, 0, 0. Negative 1 times negative 1 is 1. 1 plus 0 is 1. Negative 1 times negative 1 times 1 is negative 1. Negative 1 plus 0 is negative 1. Negative 1 times 2 is negative 2. Negative 2 plus 1 is negative 1. Now, for the third row, I try to make 0 here. So I multiply second row by 4, add it to the third row. I get 0, 0. 4 plus negative 3 is 1. 4 times negative 1 is negative 4. Negative 4 plus 1 is negative 3. 4 times 1 is 4. 4 plus 0 is 4. 4 times 2 is a. A plus negative 4 is 4. Now that's a leading one. In the third row, we have a leading one here. We try to make everything above leading one to be 0. So here I can multiply third row by negative 1, add it to the second row. So third row stays the same. Multiply third row by negative 1, add it to the second row. I get 0, 1, 0. Negative 1 times negative 3 is positive 3. 3 plus negative 1 is 2. Negative 1 times 4 is negative 4. Negative 4 plus 1 is negative 3. Negative 1 times 4 is negative 4. Negative 4 plus 2 is negative 2. First row stays the same. I get 1, 0, 0. 1, negative 1, negative 1. Once I get A to be identity matrix, what's after is the inverse matrix of A. So this identity matrix followed by the inverse matrix. Once I make A to be identity matrix, matrix I becomes inverse matrix of A. So this is inverse matrix of A. So inverse matrix of A is the matrix, this matrix 1, negative 1, negative 1, 2, negative 3, negative 2, negative 3, 4, and 4. We can check the answer by multiplying matrix A by inverse of A. If the calculation is correct, we must get identity matrix. Let's check. If we take A times inverse of A and take inverse of A times A, we must get identities. Let's check. If we take A times inverse of A, what do we get? Matrix A is 4, 0, 1, 2, negative 1, 0, 1, 1, 1. Inverse of A is 1, negative 1, negative 1, 2, negative 3, negative 2, negative 3, 4, and 4. If we multiply, we must get identity matrix. Let's try. Row times column. 4 times 1 is 4. That's 0. That's negative 3. 4 plus negative 3 is positive 1. Row times column. That's negative 4. That's 0. That's positive 4. I get 0. Row times column. That's negative 4, 0, positive 4. Also I get 0. Next row. Row times column. That's 2, negative 2, and 0. 2 plus negative 2 plus 0 is 0. Next, row times column. I get negative 2, positive 3, and 0. Negative 2 plus positive 3 is positive 1. Next, row times column. I get negative 2, positive 2, and 0. Negative 2, positive 2, 0 together is 0. Next, row times column, I get 1 plus 2 minus 3. 1 plus 2 minus 3 is 0. Next, row times column, I get negative 1, negative 3, positive 4. Negative 1 plus negative 3 plus positive 4 is also 0. Next, row times column, negative 2, negative 1, negative 2, and 4. Negative 1 plus negative 2 plus 4 is positive 1. So I got identity matrix. Next, check the other one. Inverse of A times A. I leave this one for you. If the answer is also identity, then this is correct. Otherwise, we make mistake. So check this one by yourself. Next, find inverse of B if possible. Find inverse of B. So same procedure. Write matrix B and identity matrix together. Write matrix B and identity matrix together. Matrix B followed by identity matrix. B is the matrix 1, 0, 1 in the first row, 1, -1, 0 in the second row, 0, 1, 1 on the third row. Identity matrix is always 1, 0, 0, 0, 1, 0, 0, 0, 1. We try to reduce matrix B to identity matrix. Once we reduce B to identity matrix, what we have here is the inverse matrix of B. So try to get identity matrix here. Then what we have here is the inverse matrix of B. That's our goal. Try to get identity matrix here. Then what we have here is inverse matrix of B. So let's reduce this matrix to reduce to echelon form. First step, in the first row, we have a leading one here. So that's good. Next, try to make everything below leading one to be 0. What I can do here is I can multiply first row by -1, add it to the second row. Multiply first row by -1, add it to the second row. So first row stays the same. I get 0, -1, -1, -1, 1, 0. Third row has 0 already, so don't make any change. Now let's move to the second row. In the second row, try to make leading one here. I can simply switch row 2 and row 3. If I switch row 2 and row 3, so row 1 stays the same. I get 1, 0, 1, 1, 0, 0. Switch row 2 and row 3, I get 0, 1, 1, 0, 1, 1. Row 3 is 0, -1, -1, -1, 1, 0. Next, that's a leading one. I have to make everything above and below leading one to be 0. So what I can do here is I can multiply row 2. I can add row 2 to row 3 directly. So first row stays the same. Second row stays the same. Add second row to the third row, I get 0, 0, 0. -1, 2, and 1. Now here you can see that there's no way we can make this to be identity. There's a 0 here. No matter what operation we use, we cannot make identity. We cannot make leading one here. This is a 0. Leading one is here. No matter what operation we use, we cannot make leading one here. So that means matrix B cannot be reduced to identity matrix. Since the reduced relational form of matrix B is not identity matrix, then B is not invertible. By equivalence theorem, B is not invertible. Since the reduced relational form of B is not identity, by equivalence theorem, B is not invertible. So inverse of B does not exist. If matrix B cannot be reduced as identity matrix, then we know inverse of B does not exist. We cannot find the inverse.